Yes, so I guess.
Yeah. So the plan for today is to devote almost the complete session to describing the emulator code and what it means to do verification on it, and how to prepare the code such that it is amenable for doing the kinds of verification tasks that we propose to do. Yeah, and that's what Diganta will review the code, explain what the how to execute the current version with the BIOS, and then how do we need to, why, in order to do the kinds of verification that we want to do on it, that we need to tweak a little bit, to prepare the code for that purpose, and what the steps that you guys need to do to prepare the code for that. And that is a part of your responsibility as part of the project to prepare. The preparing step would also be part of your, you will be expected to do, but the rationale for that and how you need to, what we need to do for you to prepare the code for verification will be described today.
Okay, sure. So I'll start sharing screen and just display these things. Yeah, so hopefully you can see my screen. Okay. Yeah, so I gave a brief demo of the 8086 emulator last time during the tutorial. So this is basically the emulator code over here. So this entire emulator code is there in just one particular C file. So the emulator itself is just this one C file called yeah. So the emulator itself is just one C file, which is this 8086tiny.c. And if you remember, what we had to do to run it was just build and then use the run me script or any of the other scripts that are there to run this, right? Okay, so the first thing that I want to do in some sense is to give a very brief overview of the code and where certain things are and sort of the high level description as to what the various things, like various points in the code are. So if you go and like scroll from the top down, there is includes, then there is a bunch of macros that are defined here. So there are some static defines over here, which define some constants which are relevant. But then a lot of the sort of heavy lifting of encoding and decoding, like op codes and op-amp, operands and so on, all of that, or at least a large portion of that, is done in the macro. Then things like multiplication of actual, let's say when you multiply something, the expression is actually captured inside this macro instead of it being some code of somewhere. Similarly, there's a macro for division, there is an add, subtract, macros for that, and so on. There's macros for push and pop and such things. So basically, a lot of the actual code for handling the operations are defined in the macro. This might make things a little bit hard to read, but one of the good things about EVA is that it will actually unpack some of these things for you and will show you a version of the code where some of the branches have been made a bit more explicit and the macros have been substituted and expanded and so on. So you can use EVA for that even. And you can do that without just by passing the C file through EVA without doing any, or in fact FramaC in general, without doing any modification to the C file at all. You can also use various compiler flags to sort of do just a pre-processing step that will help with the readability. You can try all of those things. So that these are some things that I would say. I mean, it's up to you whether you want to do it or not. But once you say once you realize that you're having to get into the details of what the multiplying operation is actually being defined as, then you might need to actually just go ahead and read the macro. Until then, you know that okay, mul macro is just whatever multiply is and so on, right? Okay. So here we have all the global variables. So this is written in the style where there are no local variables in any functions. Well, there is only a few functions and there are no local variables in the code at all. Even temporary variables are actually things like temporary variables, loop indices, all of those are defined right here at the top of the file. So yeah, so things like, say, you can find things like scratch, unsigned character, so it is a temporary variable. This is, I think, also IO high low is another temporary variable and so on. So such temporary variables are defined here. Apart from that, there is also some variables that represent or directly correspond to, let's say, the state of the machine as you would see it in some description of the instruction set, right? So for example, if you imagine your like x86 PC is going to have some memory, right? And that memory is being encoded as a array of characters or array of bytes, if you will. And that is also defined over here. There is this RAM size macro is defined somewhere above. So if I go to that, for example, this is being defined over here, the RAM size, and this corresponds to roughly 1 megabytes. Similarly, things like IO ports, which we don't have to worry about, are defined here. You have your registers. So these are all your 8-bit registers, and you have a separate set of 16-bit registers, and so on. You have things like some extra variables which hold some special register values, like the instruction pointer, and so on.
So the instruction pointer is actually a fancy name for PC.
Yeah, it is just a fancy name for PC. It's just what this particular ISS decides to call its PC. Specifically, it basically points to wherever the next instruction would be fetched from in memory.
Okay.
Okay. So this is basically where all of these things are being defined. And again, as I said, there is also a bunch of other variables, which are some of which are actually temporary variables internal to the emulator, and they don't really correspond to anything that will be described in some description of the instruction set or represent anything that is inside the CPU necessarily. So you have that. You have some other variables which are specifically for the graphics. So we have decided that for this, we will just compile and run it in no graphics mode for the most part. So anything that you see included in this if and if no graphics and if this sort of an environment, you can decide to ignore. But there are basically some other variables here that are relevant for the graphics. Okay, so then you have a bunch of helper functions, and these do a bunch of things which are more or less self-explanatory, and the comment lines here will give you what you need to do. So just to go over them a little bit, basically these things set some particular flags. So you have, say, for the auxiliary flag or the overflow flag and so on. So you have these flags are supposed to be in some particular 8-bit registers and in some particular, let's say, location or bit of that 8-bit register. And these functions set all of that according to whatever the new flag value you have passed in by this int. Similarly, this function will somehow this will basically read some of your temporary variables and will handle setting up, say, the overflow flag and the auxiliary flag based on whatever happened during the arithmetic operations. Okay. Right, so similarly, you have some other helper functions that do various things. So there are some instructions here which are like so for whatever reason, this particular function is here, which handles the triple A and triple AS, double AS instructions specifically in a separate function over here. Instead of putting it in a macro. I think the reason for that might be that it's like separate from list of the say groups of instructions and so on. And you have some audio callback here which you can ignore again. Okay, so this is some of the helper functions and so on. And I think the better way to do it is to basically just look at what this function is doing in whatever context they are being called, right? So you can use that. And then finally we come to the actual main method. This is where you'll have to do most of the modifications to the main method, and for the most part you'll be spending your time in the main method, right? So at a very top level, initially you have some graphics and sound related initialization which you can ignore. Then you're initializing your certain registers according to the way they would be actually be initialized in a CPU, right? So this part of the code from this 271 up until here is going to initialize things like your registers to certain specific values. After that, you are going to load the BIOS, and I'm going to be a little bit more specific about what I mean by that in some time basically I'll describe what it exactly means to load the BIOS. And you also load something called this BIOS table lookup. And once you've done that, you come to the actual execution loop of the instructions. So this is the loop that will basically loop over instruction by instruction and execute each one of those instructions. So you decode the instructions, and then based on the instruction, you go into this entire huge nested switch statement, which will do various things based on whatever your instruction is, right?
So the instruction go up.
Yeah.
So it actually executes whatever instruction that is pointed to by reg IP. Yes, that's right.
Yeah.
Yeah.
So this entire loop, the body of the loop is going to execute one instruction, and that will be whatever the instruction is that is pointed to by reg IP. Okay, so in fact, I'll get into some of the detail of that, specifically where it's fetching the instruction from memory and so on in a second. But I think just a bit before that, I want to talk about what the boot process in some sense of the emulator is, so that we can then talk about loading the BIOS and such things. Okay, so this is a description of what's happening when you boot the emulator apps. Okay, so basically, if you remember, your like, or not just this, but any general CPU basically is going to have some RAM, and then the CPU works by fetching some instruction from the RAM, doing whatever it needs to do some IO operations or some memory operations, and then fetch the next instruction and so on, right? So your program is going to, if you remember, a program is going to sit on the RAM, and the data is also going to sit on the RAM, and we have to, in some sense, decide where the program sits and where the data sits and so on, right? So the way the PCXT, or which is this particular machine that this emulator emulates, is designed is that the CPU is going to assume that when it starts up, whatever program it needs to execute, it is sitting in a particular place in the RAM. So there is some initial value of the instruction pointer or program counter, if you will, right? So initially the PC or IP is going to point to a specific portion in the RAM, which corresponds to the address 0F00, and I think it's 0F, so it's written right over here. Right, so yeah, it's 0F0, sorry, F000 and then 0100. So I'll send you the ISA file which has this written. Right, so this represents the location where the initial instruction pointer is going to be. So when the CPU starts, it's going to read the instruction, whatever instruction is going to find in this location, execute that, and then fetch the next instruction and so on, right? So the CPU is going to start executing from here. therefore, the very first program that the CPU should run is that should sit over here as well. And that program is called the BIOS, right? So the BIOS is basically going to sit in a section over here. So the BIOS that is being given with this emulator, this BIOS is around 8 KB, right? But I think in general the BIOS could be anything up to so I don't know what the maximum limit is, but it is less than 64 KB. So it was probably less than 64 KB. So this particular BIOS is 8 KB long, but you can have BIOSes of various sizes. You can have much smaller BIOSes as well. I don't know how much larger you can get, but you can definitely go smaller than 8 KB. So this BIOS would basically sit here, and the CPU is going to read instructions of the BIOS one by one and execute them, right? So it's then the BIOS's job to initialize various things, right? Because it's the very first program that's running, right? When the BIOS is being started, nothing has been set up yet. So your disk drives have not been set up yet. Your IO ports have not been set up. Your display has not been set up, right? So all of these would correspond to various chips, which are usually memory mapped to various segments. So they're looking at certain segments of memory to basically communicate with the CPU. And then the BIOS's job is to basically set correct values in those particular memory segments to set up this chip. So maybe this is like the display chip. And then similarly, you would have some keyboard chip that is also looking at certain part of the memory. And the BIOS is going to set that up as well, and so on, right? So you have these various parts of your hardware that needs to be initialized, and the BIOS is going to do that. Then what the BIOS is going to do is it's going to initialize your, say, the floppy disk drive. And it's going to initialize the floppy disk drive and then start actually copying data from the floppy disk drive into memory, right? And by data here, what I mean is that whatever OS is there in the floppy disk drive, the bootloader of that OS, right? So if the floppy disk drive has got some bootloader, it's going to copy that into the memory then. And then once the BIOS has done all of that, it will basically jump to wherever it had copied the bootloader of the from the floppy disk drive, and it's going to start executing that. At that point, you have basically started booting into your OS, and whatever OS is on your floppy disk drive is going to handle everything from that point onwards, right? So in some sense, your boot sequence basically looks like this. So your CPU is going to set instruction pointer to some specific location, right? And then the BIOS. So, okay, in an actual machine, what happens is that this particular instruction pointer, this specific location where the instruction pointer sits, the BIOS is actually a chip that replaces the RAM contents in this segment. So, for example, if you have an 8 KB BIOS in an actual machine, that means that this section of the RAM doesn't actually point to any, like if you read to it or write from it, you're not actually reading to or writing from some actual RAM chip, but instead you're reading the data in your BIOS ROM. So this BIOS read-only memory or ROM basically sits in this particular section where usually your RAM would sit, and there from there the CPU is going to read the BIOS instructions, right? So it's going to set the IP to beginning of BIOS, let's say. And this is in the real machine, and it's slightly different in the emulator, and I'll tell you how it's different. So the CPU sets the IP to the beginning of BIOS ROM, and then the BIOS takes over, right? So the BIOS then initializes a lot of things. So it initializes lookup tables, it initializes your hardware, it initializes things like keyboard, display, disk drives, and so on. It will initialize all of those things. And then the next thing that it will do is it will basically load in the bootloader. So after doing all of this, it will copy bootloader from, say, whatever floppy disk you have into some particular point in the memory. So BIOS is just a program, right? It's just some set of instructions that are according to, so basically there's some set of x86 instructions. Similarly, the bootloader is also some program. It's just a set of x86 instruction, but the bootloader assumes that all of this initialization has been done, right? So in some sense, the bootloader is going to depend on this initialization. And then the bootloader's job is to basically transition your machine into loading the OS and running the OS, right? And then you go into the OS, and then finally the OS is actually going to run programs and so on. So this is your boot sequence. So your BIOS, it doesn't assume anything other than the instruction pointer is set at the beginning of the BIOS ROM. And then it initializes everything, which allows the bootloader to assume that things are initialized and actually, use disk IO and such things to load the OS. So this is the boot sequence in a real machine, right? So is this clear? Any questions? Yes or no? Hello?
No questions.
Okay, sure. All right, so now let's talk about what's happening inside the emulator. So in the emulator, so similarly, you see in the emulator, you don't have any BIOS ROM, right? So the main difference is that instead of having a BIOS ROM, you have a BIOS file. So which in our case is basically this this particular file here called the BIOS, right? So maybe I'll do it here and then, yeah. So this particular file BIOS over here. So this represents, the raw binary data that would be present in, say, the BIOS ROM of a actual x86 machine. But this is right now is stored in a file, right? So the emulator is going to do this. The emulator is going to, after it starts, it's going to set IP. So it's going to set up some registers and other registers, let's say. Then what it's going to do is it's going to read the file, right? So read the BIOS file. And it's just going to copy that into this BIOS section of the RAM. So copy into BIOS section of RAM. And remember that this particular section is basically starts at wherever the IP is pointing to. So this is starts from IP. So this is this section that I'm talking about here. This section of the RAM. So it's going to just copy the file into this section. So if you remember, the RAM is just one huge array that is there inside your emulator, and it's just going to copy the file into that particular section. And once it's done doing that, it's going to then start executing the BIOS. Right? So okay, actually even before that, it's going to copy the lookup tables from the BIOS, and I'll tell you what these are. And then it's going to start executing the BIOS. Right? And then after that, it's basically exactly the same as what was happening in the real machines. The BIOS will execute, the BIOS is going to initialize various things, and it's going to then again copy the bootloader into memory. The OS is going to kick in, the programs will start running, and so on. So this is basically the difference in the between the emulator and the real CPU, right? So if you look at the code, this section here is actually setting the various registers, the Reg16 and Reg8. And if you remember, the instruction pointer is actually just a special register, right? So that is also will essentially be set over here. And then in this statement, it is both setting the Reg IP variable and also reading the BIOS from particular file, right? So this loop here is going to read parse your command line arguments and read files and so on. And then this one is going to disk2 is basically refers to your BIOS file. It's a C file object, and this one uses the read function to read the contents of that file into the correct location in memory. Okay. Right, and then you have this thing called the BIOS lookup table, which has been initialized. So I'll talk about that in a second. So far is the boot process more or less clear?
So I have a question.
Yeah.
So last time in the group, we were talking about basically the BIOS is a binary, right?
Yeah.
So is the program like dynamically loading this binary? And if that is the case, then how will a static analysis tool, static analysis tools don't dynamically load the other binaries, right? So how will that work?
Yeah. So we will get to that. We will get to that definitely. That is the main issue that we'll have to like deal with. But before that, I just want to describe a bit of the code so that when I start talking about that, I'll like start talking specific details of changing some pieces of code. So so that you can follow that, I wanted to just sort of give you some specific description of what the code is and so on, right? Okay, so far, any other questions regarding anything else? Like, okay, so if not, I'm just gonna describe some of the code. Okay, so yes, like I said, that this is basically where the boot process ends, and from here or rather the BIOS loading ends, and from here, the CPU actually starts executing one instruction by one instruction and so on, right? Okay,
Where is
so
the fopen for the BIOS file?
Where
is the fopen for the BIOS file?
Yeah, so the fopen was over here.
Just open.
It's in 284. This line over here. Is that okay?
Thank you.
Yeah, so it's not using fopen, it's using open, but I think that's fine. So yeah, it's basically just going to iterate over your command line arguments in this unnecessarily compact way and open one of them, like open them one by one. And then disk 2 is where the BIOS file goes, because that's the first command line argument it is supposed to pass. You can see that in the, if you look at the script which calls the executable, it's BIOS, and then this is floppy disk, hard disk, and so on. Okay. So yeah, all right. So right now the mental model that we have is okay, that over here we are setting up various initial values for our registers, and then over here we are opening the BIOS and other files. Here again, I set up some other values of the register based on the sizes of your hard disk and so on. So some register values initially are supposed to hold the size of the hard disk. The BIOS will use that information to initialize other things. So that is being set up in this particular line. Then here you're actually loading up the BIOS, the data that is supposed to be in the BIOS RAM into a certain section of the memory, which is basically reading the data from the BIOS file and dumping it into the RAM array. So now we come to this part of the code. So this is somewhat important to understand. See, what's happening is what happens during your instruction execution. Okay, so actually let's come back to this a little bit later, but let's move on to this for loop and talk about fetching instructions one by one and decoding them, and then we'll realize where exactly this particular BIOS table lookup is being used. But this is for now, this is some array that we're initializing using some of the data on the BIOS right now. Okay, so what's happening in this instruction execution loop is basically this opcode stream is where a pointer which points to within our host memory points to wherever the next instruction is going to be. So this is not an index in terms of the actual x86 machine RAM, but rather it is a pointer with, in the sense that it points to something in our host RAM, right? And this is being calculated over here with some pointer arithmetic. So if you remember, the addressing structure in x86 basically looked like this. You had your segment address and then you had your offset, right? So it looked like segment. So we would write it as segment : offset, right? And when you fetch the instruction, the segment comes from something known as the code segment, or CS. This is a particular register which holds the segment of wherever your instruction is going to come from. And the offset is going to be given by your IP. So you load your instruction from CS IP, right? And if you remember, this segment basically refers to some 64 KB sections of your RAM. So each segment is going to be some 64 KB section, and they do definitely overlap and so on. And an offset is basically an address that is within this segment, offset from the beginning of the segment. And like someone pointed out, you can obviously, particular location, actual location in your RAM can be referred to by multiple CSIP addresses. So it's not a unique way of addressing things, right? So your CSIP basically encodes whichever instruction you need to fetch next. And if you remember the actual physical 20-bit address, so the reason we need to do this is because all our words are 16-bit, but our address is actually, our RAM address is actually 20-bit. So this is a way in which we encode or encode a 20-bit address into two 16-bit things. One is a segment and one is an instruction pointer, right? So the way we do that is basically take the code segment, multiply that by 16, and then add to the instruction pointer. So this is how we take these two things and calculate the actual index within the RAM, or the RAM location which are very particular, in which our program counter is going to be. So this is basically what your PC is, right? So this bit of the code inside the for loop, this bit is just calculating this PC, right? So here you're taking the code segment register, multiply that by 16, and add the instruction pointer register, you get the PC. And then finally you add that to memory to basically get a pointer to wherever the next instruction is, right? And of course, it should not be the beginning of the memory, because that means that that is basically what the null address is in an x86 machine. So if it's a null, then you stop executing essentially. Okay, so this opcode stream then is basically points to the next instruction, and if you dereference it, what you get is a byte that will basically point to the particular opcode that is there in that particular memory location, right? So we need to talk a little bit about how instructions are stored in memory. So instructions in x86 can have various sizes ranging from, I think, 2 to 6 bytes long. So instructions can be 2 to 6 bytes, and then basically in this 2 to 6 byte, the first byte is what is known as the opcode. This is byte number 0, if you will, right? And this opcode is what is going to specify what instruction it is that we are going to execute next. The rest of these things, the rest of this basically is going to give you things like arguments, etc. Yeah, essentially it's a very complicated way of encoding arguments, because you can have various combination of arguments for each instruction or for each opcode, right? So the first step then is to basically realize what your opcode is, and your opcode as a byte is going to be given by dereferencing this opcode stream, and then you call the set opcode method with that, and that is going to do the first part of actually decoding the opcode. So let's go into this method, right? So it's over here, you're doing the first part of actually decoding the opcode, and you're setting up various internal local variables that is, holding various information about what the opcode is and so on. Okay. We'll go into a little bit more detail of that particular function later on. And then what happens is, after you've done that, so this is basically you're extracting the, so IW and ID are basically the arguments, various forms of arguments that you can have for various different kinds of instructions and different forms of the same instruction and so on. And so you extract that from, your opcode, and so the raw opcode ID is basically just this thing. So if you go into this particular function, here you're setting raw opcode ID to opcode. And if you remember, opcode again was whatever you dereference your opcode stream to be. So this is the first 8 bits of an instruction. This is also the first 8 bits of the instruction. And you're extracting some various flags from that in some sense. And then you're, extracting the other possible data that your opcode can have. And you're getting that by looking at the next bytes in the opcode stream, essentially the next bytes of your instruction. So opcode stream plus 1th byte, opcode stream plus 2th byte, and so on. So you do that, you do some more extraction of this is in a similar way you extract other various parts of your like argument encoding over here, and then you go into the actual switch case, which is switch on what kind of opcode it is, right? So this XL80 opcode ID, this is a temporary internal variable that is holding what kind of instruction it is that we are, or what group of instruction it is that we are currently parsing. So for example, 0 would refer to things like jumps, 1 refers to moves, 3 is a push, 4 is a pop, 2 is increment and decrement, and so on, right? 5 is a different kind of increment, decrement. There's also calls and so on. So you have many of these various like opcode IDs that you could have, and you're switching based on that, right? And then for each one of these, you're doing some specific kinds of things, and you can be calling your macros and helper functions, and so on over here. Okay, so not going into all of these detail right now. Let's just look at one specific function in some detail. So this set opcode. So if you remember, one thing that you should keep in mind is that this XL80 opcode ID, this thing is actually what we are branching on in this outermost switch case. This thing is basically your outermost case of whatever instruction that is you're executing. And this set opcode function is basically what sets this up, right? And if you look at this, this is actually taking this, whatever this BIOS table lookup array is, and this is an array of arrays, but we're taking certain, the XL80 lookup array, the XL80 sub function array, the XL80, the imod size table, various different tables that are part of this BIOS table lookup. And then we're looking it up with the opcode, right? To get your various, these various temporary variables that are used further downstream in the decoding steps later on. Okay. So yeah, so this is basically the level of detail up to which I need to talk about the code to finally come to answering. I think it was Siddhant who asked that question, right? That what do we do regarding actually loading the BIOS? So before that, I know that I have sort of gone ahead and talked a lot about the code without really, with some arbitrary level of detail, let's say. But at least the parts of the code in which I've shown you right now, are there any questions? If not, then I'll start talking about actually what we need to do to verify this thing.
So just one question. Could you explain, like, at a high level what that for loop is exactly doing?
This outermost for loop? This one?
Yeah. Yes.
Yeah, so this is basically extracting one instruction, like each instruction, and then executing them. So yeah. So basically, this entire code over here, right? This part, this is fetching an instruction from memory. Okay. So
more specifically, if I can interject, it is fetching the instruction pointed to by the PC, which is reg IP, the location of instruction, decoding it to see what kind of instruction it is, and then doing whatever is necessary to execute that instruction. And as a result of executing that instruction, various things can happen. And that, like changing certain registers, moving things from memory into registers or from register to memory. And at the end of the day, after that, it will move to the next instruction, which is done by by modifying reg IP. Okay, that's how. So it does whatever is needed to emulate the execution of that instruction. That's what it does. So if it's a jump instruction, then after decoding, it'll modify the PC into whatever address, for example, that it is the target address of the jump. If it is branch on some condition, it'll actually check certain flags which might have been set by previous execution of some previous instruction. And as according to the result of the previous instruction indicated by the setting of various flags, it could jump. It could either jump to a specific location or go to the next, things like that. That's what the external for loop does.
So, is it just like initializing what the different instructions are doing?
Now, what do you mean by initialization?
No, because you said that. So the comment says instruction execution loop. So
Correct.
are we executing the instructions, or I mean, I still don't
Yes,
understand.
yes, we are. It is executing the instruction.
So think of it like an interpreter, if you will, right? So there's your memory is going to have an instruction here. So, and then another instruction here, and then another instruction here, another
That's your
instruction.
program. Okay. Your
Right.
program is a sequence of instructions.
And that is sitting somewhere inside your RAM.
So it's the assembly language instruction set. Okay. Each of them is an instruction.
This is what your program is. So in fact, even in our modern x86 CPUs, this is what your program is usually, right? It's just a set of CPU instructions, some binary CPU instructions that are sitting somewhere in RAM like this, one after another, right? So initially your CSIP, this instruction pointer, is going to point to this part in the RAM, right? So this loop is going to get this instruction and then do whatever it's supposed to do, right? So let's say that this instruction is saying, okay, set the value of x to the value of, say, whatever, okay, let's say what the value of x was previously plus 1. Let's say that that is what the instruction is saying, right? So x is some register that you have, and the instruction is saying that let's set the value of x to whatever the value of x was plus 1, right? So this instruction somehow encodes this in binary, right? So this instruction is just some binary like sequence of bytes and so on. So it can be anything from 2 to 6 bytes, if I'm not wrong.
So it can be more complicated than that. See, for example, this is like, I mean, Digant is kind of oversimplifying it. Okay, but this is an assignment instruction. So in machine code, in a C, this is an assignment instruction in a C code. AX should be maybe pointing to some location in memory, say. Then you have to bring this can be translated into 3 machine instructions. One, loading from the memory into the register. So whatever if AX is an address, a variable, then there may be an increment instruction which increments and puts it in a particular register, destination register. Third instruction will be a store instruction, which will take the contents of the register and store it back in the memory location that is associated with AX. Okay. So this particular assignment instruction of C language could be translated into 3 instructions, okay, as an illustration. That would be stored here as 3 instructions. Okay.
Yeah.
And that it would execute those 3 instructions, and then it would have the effect of executing this single assignment instruction.
Yeah. So for example, so if we have that example here, right? So let's say that this instruction says something like load from particular memory location, let's say. Load from memory location.
AX, okay, you could say, I mean, yeah, I mean, AX with square bracket. It will be actual locations. Yes.
Yeah, sure. So into
something like that. Yes.
some register. So let's say that's
so the assembly instruction will not have from, etc. It will be something like LD square bracket X.
Yes, I think
that's how it.
Yes, I think it
is. It's a move. Yeah. Okay.
Yeah, move. I think so. You have to actually specify register names instead of register 0. So something like, let's say R0, and then you can say something like this. So this is your assembly syntax usually for something like this, if I'm not wrong. So you can say that, and then you can have, say, increment R0, and then you can again go move. So in the other opposite direction, right? So, so if you have 3 instructions like this, then what this loop will do is that the first iteration of the loop, CSIP is pointing to this first instruction, which is some bytes, which somehow encodes this operation that you're loading from X into register 0. It will decode that fact, realize that it needs to load from like whatever this memory location is into register 0, right? And then once it has decoded that, it will then move on to the, like, it will then change CSIP so that it points to the next instruction, right? Then in the next iteration of the loop, CSIP is now pointing to the next instruction. It fetches this, realizes that, okay, this is a binary instruction that is somehow encoding the fact that I need to increment R0. So it is going to increment the value of R0. So that will basically mean that it's going to somehow take, say, whatever. So R0 is going to be in, say, reg 16 0, and it's going to increment that, right? And then again, it's going to set CSIP to point to this particular location, right? And then here again, it fetches, it decodes the instruction, realizes that it means to move whatever is in R0 to X.
There will also be a fetch, okay? At each
Yeah.
step, it is getting the thing, decoding, doing what it is supposed to do, and then incrementing PC, okay?
Right, so it's basically looks like this. Fetch, decode, execute. Sorry. Set PC, or in this case, CSIP. In fact, it actually only needs to set IP, but yeah, and then repeat. Right. So this is the loop. Is this clear?
Yeah. Yes.
Yeah. So in fact, this is this code that I have highlighted over here is the set part, or the fetch part. It fetches, or even before saying that it fetches, it's just setting, like checking what the pointer is. And then, here you start decoding, and then here you do a bunch of decoding, and then, you switch based on what your operation actually is, right? And you do whatever the operation needs to be. So this is the execute. The switch is the execute part of it. So that is how you can think about it. Okay. So any other question regarding the specifics of the code before I go on to, the modifications and challenges of verifying this?
Yeah, maybe at this point, is it a good point to show my commute diagram?
Yeah, I think definitely, sir. Yeah. So I'll stop sharing. So if there are no other questions regarding the code, I'll stop sharing.
Yeah, I think you will have to. Yeah, you will come back to describing after I say what it is that you actually have to verify in order to verify the correctness of an emulator.
Right.
Then he'll come back. Diganta will come back and then tell you how you need to prepare this code for verification. Yeah?
Okay, so I'll stop sharing.
Okay, so see, there are two, the 3 tasks that I mentioned. Okay, the first one is the first 2 tasks are concerned with, first task is concerned with verifying what I call as design agnostic properties. Okay, such as if the code itself, the emulator code itself has, overflow, underflow, and those kinds of problems, and then checking using CBMC to eliminate it. So what I'm talking about here is the third task of how do you establish, you want to prove the correctness of whether the emulator, the C code implementing the emulator, is actually executing correctly each instruction as per what the 8086 manual might prescribe it to execute. Now, I said that, okay, one way to establish that was to prove one instruction at a time. There was also a question, a very good question, as to if you prove one instruction, that each instruction is executed correctly, why do you need to prove all programs? That's a very good question. Okay, and you may not need to. Okay, if indeed you kind of, in the most general sense, you establish this correctness criteria that I'm going to be describing in this, what I call as the commute diagram. Okay, so so this trace at the bottom here, where if you can see my cursor, is the actual execution of the emulator. Okay, there'll be some initial things that you will have to do. Maybe you will do certain initialization, etc. In the emulator. Then you get the emulator into a certain state S. What is the state S of an emulator? It's all these variables that Diganta showed. That it maintains to like the RAM, the registers, the reg IP, the CS IP, which shows indicates the current PC and so on. And then each step, what I call here, is the result of executing one iteration of that outermost loop that Diganta illustrated, which itself can have several smaller steps like fetch, decode, execute, etc. Okay, so it can have a whole sequence of C code in the emulator that gets executed. So by each step, I'm denoting the result of executing one iteration of that outermost loop, which corresponds to executing one instruction that is pointed to by the program counter location, which is reg IP, CSIP, or something that Diganta called. So now, so that is the actual. So this arrow down here that my cursor is moving from S to S prime denotes the effect of executing one instruction from an arbitrary state, which you get after having executed some arbitrary number of instructions. Now, I'm assuming that each instruction is actually specified independently of how this emulator, this particular emulator implements. And that's what I call as an independent semantic description of each instruction. That's like defining the structural operational semantics. You remember that right in the beginning of the course, we developed structural operation semantics, which described what the effect of executing, how you could specify the semantics of executing a program in a programming language, okay, for each instruction. Here it's much simpler in the sense that each instruction corresponds to an assembly instruction. Okay, so that you could specify. Say I'm assuming that we'll have an independent specification. Okay, and how do we do that? Of course, the emulator has lots and lots of details embedded in this state, but from a external user's perspective, there are certain components of that state that are relevant, what I call as the externally visible relevant parts of the state S, and that's what it denotes by SCAP. Now that is usually a projection. This alpha that I've shown here is like a projection of S. You're only taking some components that you care about, okay? Like the PC, like the memory, the RAM, and some of the registers, and including some of the flags which store some essential information of the history of having executed, the result of executing the previous instructions. Now, using that's if you looked at an instruction set architecture manual of 8086, that's how it is described. It has a table, and for each instruction, it tells what how that instruction, executing the instruction, what effect it will have on the various components of the programmer visible component of each of those instructions, like the load, store, and increment, the move instruction and increment instruction that Diganta showed. Okay, so I'm assuming that there is an independent specification, and that's what I denote as SOP step. Okay, that is what as a user, or if as a user we have to specify. Okay, that you have to specify, and your correctness of your emulator will be compared with respect to that specification. So what this says is, you start from an arbitrary instruction S for all S and S cap, where if alpha S, I'm sorry, this should not be alpha. Alpha S is equal to S cap. Okay, on the right side it should just be S cap. If S cap is the projection of S, you get by projecting some components of S. Okay, that's the case, and then you execute your E step on your concrete state, if I may call it, and then you take alpha on S prime, then that should be equal to the result of executing your semantic levels step. Okay, this will be described as, oh, if my current instruction is move, this is how it will be. There, if it is increment, it will be something. That's how this step will be specified. Okay? Which is exactly, for each instruction there will be a definition of what that SOP step is, and that will transform S cap to S cap prime. Okay? And then, so this is the, and then you have to show that these two things are equal. So this is can be described as a single function which will be applying, which you can write in C also, C itself. And here, each step will be executing that one iteration of that outermost loop in your C. So at the top level for the task 3, this is what you will be capturing. Yeah, and that you'll be verifying maybe for a small set of instructions that we will be giving you. For that, you have to, for each of those in that set that we give you, you have to describe its high-level semantic description. That is like the specification, expected specification of executing the instruction, and then that you'll have to compare with the result that you get actually by running the emulator to execute that the same instruction in reality. Okay, this is what you need. But even to do the first 2 tasks of checking certain design agnostic properties, you will still need to prepare the code. Okay, I mean, basically that's what it's actually a simplification. Okay, through that thing, preparation step. Okay. Any questions here? Okay. Okay, so we are at 3:04. Okay, so they usually, you guys need to go. You have class at 3:15, right? So 5 more minutes. Okay, is that okay? Until 3:10. Is that okay? You have to.
Yeah.
Okay, thank you. So who are all left here? Harsh has also left. I don't know. I mean, you want to rush it through, or you want to wait till?
I think let's just talk about the code changes.
Okay, so fine.
first.
Yeah, we'll finish it up, and then it gets recorded. And therefore, yes, please, let's do it.
Okay, so are we talking about the code changes now, or should
Yes,
we continue?
yes.
Okay, sure.
Yeah, but mindful of time, okay, because they have a class at 3:15, so 3:10.
Yeah.
No, the next class is at 3:30. Your class ends at 3:15.
So you have time. Oh, okay. So we can go to 3:15 then, because some people say that they'll have a class at 3:15. Therefore, I've had feedback. Okay. You have 10 minutes. Then.
Yeah, okay, sure. So yeah, so basically there is so the changes that we need to do is basically to work around a point which I think Siddhant has raised a couple of times now, which is that, see, both EVA and like CBMC, neither of those will actually go ahead and read and load in the details of your BIOS file, right? So firstly, when you're saying that it dynamically is loading this file, what it's doing when we're running it is basically just reading the contents of the file and putting it into the memory, right? Now, EVA and CBMC both have their own definitions of read for the purpose of verification. But see, at no point does it actually take some real file that is sitting on your disk and verify it against that. What it will assume is it will treat this read statement as if it was some sort of an input statement, and it will try to verify whatever you're trying to asking it to verify for any arbitrary input values, right? So that means that it will try to sort of verify things for arbitrary BIOS says that you could have, right? It's not going to verify anything against one specific BIOS, but rather it's going to verify everything against like it's going to assume that the values in the BIOS chip could be, or the BIOS section of the RAM could be any arbitrary value, right? But that is an issue because critical to actually decoding our instruction in this particular function, in fact, we can see, and there is this variable does occur in some other places as well, but critical to decoding our instruction is this particular variable, this BIOS table lookup, right? And this variable is actually being loaded, the contents of this array is actually being loaded from inside the BIOS, right? So the BIOS, if you look at the BIOS assembly code, it's got some lookup tables right here. So this is the BIOS.asm. This is also there in the in your repository. So if you look into the BIOS source folder, you'll find this BIOS.asm file. This is the file which is compiled into the BIOS binary, right? Or assembled into the BIOS binary. And if you see that these got some of these RM mode tables and these opcode decode tables, these are the sort of tables that your this BIOS table lookup variable is going to contain, right? So the BIOS table lookup variable, it's actually going to read from this particular location in the BIOS binary, which is the location in which these tables will end up in, and it will basically fill up the BIOS table lookup array with those tables, right? So basically what's happening is when this BIOS.asm is going to get compiled or assembled into this BIOS binary, all of this data is going to be put into a particular location in the binary verbatim. And now this BIOS table lookup is going to take this data that is there in this various portions of the BIOS binary, and it's going to copy it into, this two for loops was what it's going to do is going to copy this data that is there in the various portions of the BIOS binary into this BIOS table lookup array.
And I guess that information that it copies into that table is presumably needed to during the decode phase.
Yeah, it is needed, because if you look into the set opcode, it's actually calculating this XLAT opcode ID and all of these other parts of the opcode by looking up the BIOS lookup table using your raw opcode ID, if you will, right? So this is very much needed for the decode process, right? So if you aren't loading the BIOS, then as you might imagine, this BIOS table lookup is actually containing some garbage data, right? So you're verifying everything against a garbage lookup table, which means when you're verifying whether or not your instructions are working correctly, your decode process is actually never going to work correctly or never going to be simulated correctly inside your CBMC or EVA when you try to verify anything. If you leave the code unchanged, right? So you can't depend on this read loading in the BIOS and then the BIOS table lookup being loaded in from the BIOS that you have just read, right? So you can't depend on that at all. What you have to do is instead you have to somehow manually set up this BIOS table lookup by looking at the BIOS.asm, right? So this is the first change that you need to do, and I'll talk about this, and I think after that the 10 minutes might be over. But this is the first change that you need to do before even passing it through Eva, which is that you'll have to change this this or remove this particular for loop that you have.
Yeah, and I think one of the motivations, there's several motivations here. We want to make all our verification exercises kind of independent of the BIOS. Okay.
Yeah.
Content of the BIOS. Okay. And that is one of the one of the reasons. So we don't care about all the drives. I mean, the input output instructions and so on for which it is needed, and the OS details, etc. We want to verify directly, okay, what the thing is. And additionally, because the verification tools don't recognize these file reads, we'll have to find a different way of extracting the required information from the BIOS. Okay.
Yeah, so see, basically our eventual goal is going to be just to cut out the BIOS entirely. We're going to eventually get rid of this statement as well. But before we go into that, the first step, which is what I'm going to talk about right now, is basically you're going to remove this particular for loop. So get rid of this bit. And then instead, you're going to set the BIOS table lookup variable manually according to, or, basically you're going to set it manually up as a static array according to the values that are given here in the actual bios.asm file, or you can also copy it from the BIOS binary using a hex editor if you prefer that. So if you look at the code, it's basically loading a particular location of the BIOS, right? So this bit here is actually loading a particular location of your current memory, which corresponds to a particular location of the BIOS. So you can figure out what part of the BIOS or the BIOS binary that is being loaded into the BIOS table lookup, and you can just copy and paste that part in manually as something like BIOS table lookup equal to something like this, right? You can also write something like a small Python script to do this if you think if you prefer automating it. It's not, I don't think it'll be too hard to do that as well. Alternatively, you can take each one of these BIOS tables. So if you look at the way the BIOS table lookup is used, I can take 20 possible values. And if you look at, say, for example, inside the set output function, right? So you have various different kind of BIOS table or various different kinds of BIOS lookup tables that that are going to be loaded in, and those are again listed over here, right? Lookup tables in the BIOS binary and so on. And what you can do is you can manually actually go ahead and copy those particular tables from the BIOS binary in. So for example, if you have a table xlat or xlat output, then what you can do is, okay, let's say that we set something like this, BIOS table lookup, let's say table, this is going to be this thing, where this thing you can just copy from, say, this line, right? So something like this. So you can do this, and you can repeat this for each one of those tables that are there in the binary. So this is in line 3810 in the BIOS.asm BIOS source. Or you can also get it from the BIOS binary by figuring out the address in this particular line over here, that is 297 in this C file, right? So you can do that and replace this BIOS table lookup with a statically defined array. And that way you won't have to actually depend on any of your verification tools having to load the BIOS to capture the actual semantics of various instructions, right? So once you make this change, make sure that the actual emulator is still running, right? Still run the runme script and see that everything is running. Getting the prompt. You can still check that graphics and sound and everything like that is working, right? So you should still check that all of the previous behaviors of the emulators are unchanged as far as you can observe them. And then we are going to formally verify this particular modified version of the emulator, essentially, where we are, instead of looking up the BIOS table from the BIOS, we are actually hard coding it into the code, right? So, any questions at this point? If not, then I think we'll stop.
So
Yeah.
other than this BIOS table lookup, is there any use of the BIOS file?
So the BIOS file is serving two purposes. One is the BIOS table lookup, and the other is to actually give you what code you're going to start executing. It's also the very initial code in this boot process, right? So in this sort of boot sequence that we had, it's this very initial code that is being executed. So the BIOS is actually serving that purpose as well. But when we're going to verify, what we're going to do is we're going to replace this. We're going to replace this entire part, which is basically something that the BIOS handles, and then you're going to pass it to the OS and the programs and so on. We're going to replace this entire part with some set of assumes on.
Pretty much what we will assume is, since we want to verify whatever, whether the program, design agnostic properties or actual things, since we want to verify over arbitrary, we'll say, well, our memory can have, any instructions there as long as they are legal instructions, okay? Something like that. Or if we want to only verify for a subset of ISA instructions, we'll say, oh, it can contain, via these assumes, whatever instructions that we care about, okay? And nothing other than that. Or if you want a particular program, we will actually say it will actually be that, okay? So that kind of a thing. So additionally, since BIOS is also serving this one that Diganta just now explained, and since you're removing the BIOS, you will have to do accomplish that part of the task through assumes.
Right. So does that make sense?
Yeah.
Yeah. So initially for the EVA step, the first EVA bit of the task, basically, you'll just have to replace one of the functionality of the BIOS, which is the BIOS table lookup, right? So once you replace the BIOS table lookup, if you run run this C file through EVA is actually going to be able to capture the precise way in which the opcode is being decoded and so on, right? The actual opcode decoding behavior EVA is going to be able to see, instead of it having, like, assuming that the lookup table is some arbitrary data and the opcode can be decoded in some messy arbitrary way, right? So it's going to actually give you, or actually take into consideration, the opcode decoding code that is being written over here. And then you can still leave this read statement in, at which point you'll basically be verifying whether certain design agnostic properties, some things like overflow and underflow, whether they can happen for any BIOS, given that the lookup table is actually correct, right? So you have taken the lookup table outside of the BIOS, that you're hard-coded in the lookup table. So you're assuming that the lookup table is correct, as it's been specified in this particular BIOS. And then since you're leaving the read in, EVA is going to still assume that you're loading in an arbitrary BIOS, and it's going to say that, okay, if your BIOS was some arbitrary data, could an overflow and underflow somewhere happen inside of the emulator code, right?
Yeah, but that's after the first task, we'll have to remove this, right?
Yeah, so after the EVA task, the first and second task, when you come to the third task of verifying specific instructions, then you're no longer going to read any BIOS data into the RAM and do such things, right? You're going to just replace this entire thing with some preconditions or some assumes representing the state before the instruction, and then some assumes or some asserts about this, what the state after the instruction should be, right? So
yes,
yeah, that's what's going to happen there. And then that you can do, like, on a per instruction or per group of instruction basis.
Yeah, I have a small, kind of doubt. I mean, I'll elaborate because we're already running out of time. So even though, even for the EVA, like design agnostic property verification, I'm not so sure if we may still need to have certain assumes. Okay, because when you leave, BIOS is giving a particular BIOS. Okay, whereas if you don't, if read can read in anything, unless you may still need to make certain assumptions that some parts of your memory actually have. Okay. I don't know. Okay,
Yeah, that may happen. So
happen, but
that may happen, but let's see what happens. So maybe the BIOS is doing some critical initialization that without which the emulator actually is going to run into an overflow, right?
So that part, yes,
Yeah.
that part.
Of course, yeah, that part we'll have to explore, I think. But of course, one thing that is very clear is that with an arbitrary BIOS, you're not actually expected to, the emulator is not going to run any meaningful program, right? Like the actual program that is there is basically just garbage.
Let's discuss that. I don't. Yeah, I mean, I have a couple of issues. That is true, but if instead of BIOS there is junk there, then I don't know. I mean, it may start executing, thinking that it is a BIOS, and it could be a junk instruction.
Right. But it should still not overflow or underflow, right? So it will probably, the CPU will probably go into some error state, but the emulator itself should still not crash, overflow, or underflow. That is what the thing that we're checking is.
Let's see. So, but if the emulator is not robust enough, then it's
I
think we're going beyond our time. So let's
let's stop. Yeah.
So good. Thank you for your patience. Okay. So
Yeah, thanks.
you reserve your questions till next time. So.